Hello, this is Professor Dan Kernler again with our Calc 3 sequence. In this video, we're going to talk about section 16.4, which is, it says triple integrals? Okay, we did double integrals over a rectangle, fine. Double integrals over a weird, like, general region, okay. Double integrals with polar coordinates, fine, that's easy. Triple integrals, though, that's it. Nope, not doing it. Sorry, just get a little crazy here. Shut into my house. It's a global pandemic. Feel a little goofy. Okay, so we're going to talk about triple integrals and explain how that can be useful. And I have to apologize in advance. I had made a note for myself after last semester that the order of these notes didn't really make sense, and then I forgot to change it, and so we're going to go a little bit out of order and, in fact, totally skip the first example. So let me move on, actually skip all the way to the next page and talk about the development here. This is really the development of what a triple integral is. So we know the integral from a to b. It means the length of the interval. So all this is you're just integrating from a to b of dx, and what you get is the length of the interval. And we know if we integrate from a to b dx and then c to d dy, what that gives us is the area of the region. So a to b on the x, and then c to d on the y, and we get the area of the region. So it follows then that if we integrate and add another integral dz, that would give us the volume of the region. What that would be then is, see if we can draw a quick picture of this, x, y, z. And we're going to go from a to b on the x, from c to d on the y, and then from e to f on the z. So let me see here. I'm going to draw. There's what it would be in the xy plane, but then we're moving up from that e units. So here's the base of it. You know what? I should do these. I erased too much. I should do these in a different color. I've got all the fancy colors here. So we have to move up e units because of this e. So we're going to do, here's the base of it. And then it's f units tall, whatever that looks like. So it's this cube, right? It's this cube where you have the side here is b minus a, the side here is d minus c, and then this side here is f minus e. Actually, let's just, yeah, that's fine. That's fine. We'll just call it like that. Okay, so that would be the volume. So what we're going to look at now is, what does it mean if we integrate over a region? So the idea here is that we have some domain that we're integrating over, and here we're representing it by like some kind of triangular region just in the first octant there. And then we're looking at little cubes that would be some delta x width here, and then a delta y here, and then a delta z here. And we'll say this is the ith little box, not cube. It's not a cube. The ith little box. And the volume of that little box would be delta x sub I times delta y sub I times delta z sub I. And suppose there is a function that is a function of the x, y, and z position. So there's a function that's a function of its coordinates in 3 dimensions. We're going to put in the middle of this box, we're going to pretend that's in the middle. We're going to say we have a function value. We're going to say we have a point that is x sub I star. Ooh, I need to go below or to the left or something. I don't have space over there. So there's some point here that is in the little box. X sub I star, y sub I star, z sub I star. So I don't know if that's on a corner or one of the corners or in the middle of somewhere. It's just an ordered triple that's in my box somewhere. And so then I have a function that's a function of those coordinates. Now that function might be like temperature. So there's a temperature that depends on your location in space. That's kind of the easiest example. So what we could do then is we could say, well, what happens if we add up the function values at that point, and then delta v sub I, and then we're going to add up n of them. So we're going to add up 1 to n, and so there are n little boxes that we're all adding up. And then what we'll do is we'll take the limit as the largest box goes to 0. I think your book just does, sorry about that, I think your book just does 1 vertical line, the magnitude of that. That's called the norm. I think we've talked about this before, but that's just representing the largest one. So as the volume of the largest box goes to 0, what we would get then is we would get a triple summation, a triple integral over the region D. It's not R now, it's D. A different letter here because it's representing 3 dimensions, of the function f of x, y, z dv. And that's what a triple integral is. And what that function is doing is it's adding a weight for each of the little boxes. So each little box gets a weight, and then it adds them all up to get the total weight of that function over the interval. So for temperature, it's kind of a weird one. Maybe temperature isn't a good idea. Maybe it's mass. So maybe you have a function that's a function of how dense this object is per cubic centimeter squared. So you find the volume, delta V sub I, and you multiply that by that density per cubic centimeter, and what you get is a mass. And then the integral adds them all up, and so what the integral would represent there is total mass. That's what that would represent. So now, this is why I said I apologize, things are in the wrong order. We're going to go back and fill in this box here. So a theorem for triple integrals. If f is some continuous function over the region, now we're really flexible here. X is going from a to b, but then y, let me go up here. Y goes, and this one looks kind of like an ellipse, but y goes from some bottom function here. I think we use g of x in your text, and then to some top function, left and right, top and bottom, whatever you want to think of for y. That's h of x. And then z goes from some bottom function to some top function, where here you have capital H of xy is the top, and then capital G of xy is the bottom. So the triple integral would be, let's see, make sure I get the right notation here. Triple integral over the region D of f of x, y, z dv, which would be the integral, kind of spacing these out a little bit. Let's do z first. So dz, we're going to integrate the function of x, y, and z. So z goes from the capital G of xy up to the capital H of xy. And then y goes from G of x to H of x, and then x is last. It goes from A to B. What I like to think of sometimes on these is imagine that you're going to go and you're going to pick some little box here in the xy plane and then add up between the two functions. So what you're going to end up with is a little cylinder here, or a little tall, skinny, like pillar. Okay? So you're going to end up with this pillar in the middle between those two. So that's adding up the z's. The z's, the little delta z's, go from the bottom to the top, and you add all those up, you get a little pillar. Then you're going to add up those along the y-axis. So then you're going to add them up along the y-axis, and what you'll end up with is some kind of little slice. Okay, but that slice depends on x, so then you're going to add them up along the x-axis, and you get the full the full region when you're done. So first you get a little pillar by adding up the z's, then you add those up along the y-axis, you get a slice of bread, then you add those up along the x-axis and you get the full region. We should say here, if we just integrate the function of 1, so if we just integrate dv, what we get then is the volume of the region, D. So let's do a couple of volume examples. I think we'll try to do, let's see, how many examples do we have here? Yeah, I think we'll try to do 2 in this video, and then we'll do the rest of the examples in the second video. So let's try this one. Let's use a triple integral to derive the volume of a sphere radius a. The way we're going to do this is simplify our life a little bit. Instead of finding the volume of the full sphere, what we will do is find the volume of like the first octant of the sphere. So the full volume will be 8 times the triple integral over this region dv. Okay, so now our challenge is to figure out what that triple integral is. So imagine again you have a little rectangle in the xy plane. You're going to add those up vertically. You get this little pillar. So z goes from the xy plane from 0 up to the surface. Well, it's a sphere. X squared plus y squared plus z squared equals a squared. So if we solve for z, z will be the square root of a squared minus x squared minus y squared. Now, normally you'd have a plus or minus there, but we are just looking at the top half. So setting up our integral then, we're going to need some space here. Z is going to go from 0 to the square root of a squared minus x squared minus y squared. That's going to be dz, then we'll do dy, then we'll do dx. Okay, so we added them up from 0 up to the surface. Now we need to add up the y's. So the y's are going to go from 0, we're going to add them up this way, 0 over to, you see the little slice there? So now we're going to add them up from 0 over to the curve, but we need that curve. And that curve is in the xy plane. X squared plus y squared equals a squared in the xy plane. And so similarly, y is the square root of a squared minus x squared. So that will be the interval for y, 0 to square root of a squared minus x squared. And then finally the x, we're going to add up those slices, and x goes from 0 out to a. And that, once we evaluate it, will give us the volume of a sphere. Very inefficiently, I might add. This is not an efficient way to find the volume of the sphere. Okay, now I am going to cheat and realized I should have put this stuff over here to give myself more workspace. Well, let's see here. Okay, all right, let's go now. Let's see. Well, let's integrate, let's do that first integral. 8 integral from 0 to a, square root, or 0 to square root of a squared minus x squared. The integral of dz will just be z from 0 to the square root of a squared minus x squared minus y squared. And that's dy dx. And so we'll plug in the upper limit, subtract 0. So all we'll have then is 8 times the integral from 0 to a, square root of 0 to the square root of a squared minus x squared, and then square root of a squared minus x squared minus y squared. And that's dy dx. Haha! Now you should be thinking, wait a minute, this is an integral over this region. This is a circular region. Polar. Use polar. Oh, I don't know if I left enough space. Oh boy, this might not be good. Okay, theta goes from 0 to pi over 2. r goes from 0 to a, and then you'll notice I have the square root of a squared minus r squared. If I factor out a -1, you get x squared plus y squared. And then I have r dr d theta. So I've changed coordinates to polar coordinates. That looks pretty good. This will be u equals a squared minus r squared, du equals -2r dr. So this will be 8, and then I've got a -1/2 integral from 0 to pi over 2. And then, let's see, u at 0 will be a squared, and then u at a will be 0. Okay, so now this is integral from a squared to 0 of square root of u du d theta. I already took care of the r dr by dividing by -2, so that gave me the -1/2. Okay, that's -4 integral, actually let's make it +4 integral from 0 to pi over 2, and then I'll have u to the 1/2, no, u to the 3/2 divided by 3/2, so 2/3 u to the 3/2, and then I'm going to switch the bounds, 0 to a squared d theta. This is so funny. So I did this last semester. Here are my notes. You'd think I would have learned, whoops, over here. You'd think I would have learned to add more space. Nope. Okay. What do we have here? This looks pretty ugly. 8/3. And then we're going to plug in a squared, but then we're going to do to the 3/2. So that'll be a cubed d theta. Okay, that's 8/3. A cubed theta from 0 to pi over 2. So 8/3 a cubed times pi over 2. Oh, awesome. 4/3 pi a cubed, which is the volume of a sphere. So this was not an efficient way to find the volume, a formula for the volume of a sphere, but it does confirm what we already knew. Oops, sorry, I should scroll down there. It does confirm what we already knew about the volume of a sphere. Okay, next one. And then we'll call it a video here after this next one. Use a triple integral to find the volume of the solid bounded by z equals square root of 1 minus x squared, the xz plane, the xy plane. Oh, you cannot see that in the video. Z equals square root of 1 minus x squared, the xz plane, the xy plane, and this is not the line. That's not the line. It's the plane y equals x. Okay. Well, we are only in the first octant because we are bound by the xz plane and the xy plane, or the xy plane, xz, xy. Okay. Whew. And then, boy, y equal x, y is equal to x, so z is fixed there, right? So that will just be y equals x. I think I need, that's just going to be a plane like this, right? Just a vertical plane there, y is equal to x. No, that is not good. That's not y equal x. Y equal x would be at 45 degrees here, right? So it's basically there's a plane coming out from the z-axis. And then square root of 1 minus x squared, y is free there. So that one means it's going to be a cylinder along the y-axis, and it's a cylinder in the shape of a semicircle, actually, right? And then it's kind of moving out this way. So we are bound by those. So my guess is then we're going to be, maybe can I draw, I don't know if green is a good idea. So right here is the region we're going to look at. Let's take a look at that. I have a maple graph of this. Oh, there, that looks much better than my drawing. So you can see here the yellow is the plane, y equal x, the blue is the cylinder. And we're just going to look at, we're bound by the xz plane, the xy plane. So we're looking at this volume over here on the left. And that's going to be important when we set up our bounds. I'm more interested here in the setup, so we might shortchange the integral here to focus on the setup. Okay, all right, we have our representative piece. We're going to add up vertically to make a little cylinder, so we're going from 0 up to the surface. Z will go from 0 up to square root of 1 minus x squared. That's going to be dz. And then we have dy dx. Okay, in the xy plane, we have this region right here, xy plane. And so what do we have here? This is y equal x. And so when we add up along the y to get that slice, we're adding up along the y. Right, we get this slice here. So y goes from 0 over to the line y equal x. That's y, goes from 0 to x. And then x will go from 0 to, where do they intersect? Ooh, I don't know, I'm assuming it's 1, right? When x is 1, z is, that's where they intersect? When x is 1, yeah, when x is 1, z is 0. So that's 1 there, so 0 to 1. That looks good. All right, that integral is actually pretty straightforward. So I think I'm going to just kind of write that. If you're interested, it should be 1/3 when you are done. This would be a great check. This kind of problem is a reasonable test question. It's not crazy difficult. The integration is reasonable. Sometimes tests can get really long if you have this crazy integral. And really, I just want to know, can you set up the triple integral? So I might ask you to just set some up, but if I do have you to compute one, it might be one like this. So that is it for this video. We will pause here, stop here. And in the next video, we're going to do a couple more volume questions. And then we're going to do a last one where we're going to do an example of temperature. We're actually going to find the average temperature of a cube of metal that's been heated and has different temperatures throughout the cube. So that is it for this video.